right. First of all, you have to know your method for factoring. I, again, am a guess and checker, but if you do slide and divide, that's fine as long as you're good at it, okay? You need a method, whatever it is, you have to be able to factor something like this. Like I said, I'm a guess and checker, so I would start with my prime number here because it only has one option, 2 times 1. One of those has to be negative, one of those has to be positive. And when I multiply it with the x's out front and add those together, I need to get an answer of -1. And so 15 and 1 were not going to work. My only other options for factors of 15 are 3 and 5. So I just had to figure out how to fit 3x and 5x in here so that when I multiply my outsides and insides, I get a -1. Well, I ended up putting my 3x here and my 5x here so that I get 6x and 5x because those are 1 apart. I need it to be a -1, so I made my 6x negative, my 5x positive, which would give me a sum of -1. Then we set each of those equal to 0 because it did ask me to solve. Add 2, divide by 5, and I get an answer of 2/5. Subtract 1, divide by 3, and we get an answer of -1/3. Kind of putting all those together, solving our polynomial is the same thing as finding the zeros of the polynomial. It's kind of whether you are looking at it graphing wise or as an equation, whether we call them zeros or solutions or roots. It's kind of all the same ways of asking for the same numbers. And it's just kind of dependent on how your polynomial is set up to begin with. Today, what we are going to accomplish by the end of this is being able to evaluate a polynomial using our remainder theorem. It's going to be a method that will help us speed up our process is essentially what's going to happen, which is nice, especially having a calculator. It's a process that can help us speed up. And then factor theorem also is a way that is going to help us be able to find answers to something that we cannot factor. Okay, so they'll hand us a polynomial that at the beginning we wouldn't be able to necessarily factor, but we might know something about it. And using this thing that's called the factor theorem will allow us to work it down to something that we can factor at the end. All right, so remainder theorem. What does the remainder theorem say? The remainder theorem says if we've got a polynomial, f of x, and we divide it by x minus c. So that's what we were doing in class yesterday, right? We learned 2 methods for that, long division and synthetic division. What it says is the remainder of that process is the same as if we were to plug c into the function. So what I want to show you is this happening side by side. Yesterday, we learned a method for how to factor a polynomial, or sorry, not factor, how to divide a polynomial using synthetic division. And so over here, I want to divide this polynomial by x minus 2 using synthetic division. So if we do that, I would set up my coefficients, 1, -4, 5, 3. And then what number goes on the outside here? 2, right? That is like a 0. So remember, we are looking at this is called a factor when it has that x minus 2. And when we look at it in this format, it's a 0 of our function, right? Because we would have set it equal to 0 and solved. I do my synthetic division by dropping down the 1. 2 times 1 is 2. Combine my terms. -4 plus 2 is -2. 2 times -2 is -4. Plus 5 is 1. 2 times 1 is 2. Plus 3 is 5. Right now, that's all we're going to do is I just want to show you the dividing process. We're not going to write out an answer or anything because I want to show you what this remainder theorem is saying. Okay. So now hold on to that and let's go over and evaluate f of 2. F of 2 says plug 2 into the function, right? So let's go ahead and do that. F of 2, here's our function. I'm going to plug a 2 into all of those places. 2 cubed minus 4 times 2 squared plus 5 times 2 plus 3. which if I have a calculator, I could just type all that in real quick. I don't have a calculator in my hands, so I'm going to keep doing this by mental math. 2 cubed is 8. 2 squared is 4 times negative 4 is negative 16. 5 times 2 is 10 plus 3. 8 minus 16 is negative 8. Plus 10 is 2 plus 3 is 5. How'd my mental math go today? So it's always a little questionable, so you got to check me on that. Okay, now what you guys are seeing side by side is the remainder theorem. Key in on the word remainder, okay? Look at the remainder when we divided by x minus 2. Our remainder was 5. What was our answer when we plugged in 2? 5. Is that a coincidence? No. That's exactly what this theorem is saying, is that if you were to plug in the same 0 that you divided by, your remainder is the same as your answer. So why do I use this? Well, guys, we're actually going to use it kind of in both directions. Sometimes it's actually easier in smaller numbers to work with doing synthetic division. So it actually could do this for me. By doing synthetic division with smaller, like working with synthetic division can be smaller numbers. Sometimes I want to do this to help me find zeros, and I want this answer to be 0 to tell me if it's going to work over here, okay? So using it both directions in the remainder theorem, the fact that our remainder will match our answer if we plug that in. So we'll kind of see it both directions here. So let's look at this question carefully. Given that our function is f of x equals 3x cubed plus 4x squared minus 5x plus 3, use the remainder theorem to find f of negative 4. So f of negative 4 initially tells me to plug in negative 4, but then I have to go figure out what negative 4 cubed is and multiply that by 3, and it ends up being really big, ugly numbers. And so the remainder theorem also tells me that I can just do synthetic division, and my answer will end up being whatever I get for my remainder. And when we start like cubing numbers or raising them to the 5th or something, raising something to the 5th ends up being some really big, ugly numbers. And if I don't have a calculator, doing synthetic division might be my better option. Now, here's the key to this, is if they tell us the 0 is negative 4, notice I am not changing the sign on that, right? If we go back to our remainder theorem, remember or notice that the number inside of here is the number that was outside of our synthetic division. That throws people off, but that is the 0, right? That is not a factor, so we would not change the sign on it. So coming back over here, doing my synthetic division. Now notice, I don't have a calculator, and I can get through this one mentally without a calculator, because I can do negative 4 times 3. I can do 4 plus negative 12. These are all pretty easy numbers right now to work with. Negative 4 times negative 8, that I should be able to do, right? 32. I can add 32 to negative 5, or 32 minus 5. This one, okay, so we might have to slow down a little bit here. 27 times 4, 4 times 7 is 28. Carry the 2. I can do this, right? 4 times 2 is 8, plus 2 is 108. Okay, that one took a little bit of time. Okay, but add those together, and it looks like I get negative 105. Good. Okay, so what did I just find? I found this. I can now say that if I had plugged in negative 4, I would get an answer of negative 105. I would get an answer of whatever that remainder is. If the directions specifically ask you to use the remainder theorem to evaluate this, they are not asking you to plug negative 4 into the function. They are asking you to do your synthetic division and identify your remainder. Now, those are the same answer. So could I check myself by plugging it into the function? Yes. I would not do this. But if I were on a test and I wasn't sure that I did this correctly, could I? But look at what happens on this one. F of -4 means I'm doing -4 cubed. And do you know what -4 cubed is off the top of your head? And then you have to multiply that by 3. So do you see how this is already getting to be ugly numbers? Which I only had to like slow down one time when I took 4 times 27. You're gonna have to do a lot of work here. And then again, -4 squared times 4. But you could check yourself that way. I would not, but you could. Questions on that? Okay, so again, please understand that when they ask you specifically to use the remainder theorem to find this, they are asking you to do your synthetic division and identify your answer as your remainder and your remainder only. So -105 is the answer. Okay. The factor theorem kind of takes into account that remainder theorem, except for if it is a factor of our polynomial, when I do that, I get an answer of 0. Because the remainder when I divide, and it is a factor of my polynomial, meaning when I put it into full factor form, it would show up in that list. The remainder is 0. And so notice both directions. If I were to plug in C for x minus C, I get an answer of 0. And if I were to divide it using that, then I get an answer of 0 or a remainder of 0. And again, this one we will use both directions here. Sometimes we will plug it in to see if we get a 0 to know what to try out. Sometimes we will divide and look for a remainder of 0 to know it's a factor. But the key is remainder of 0 is a factor, and a factor has a remainder of 0. If I flip back a page here just to kind of show, since we've already done the work here, this would have been the equivalent of x plus 4. Because our remainder was not 0, x plus 4 is not a factor of that polynomial. You see what that factor theorem is saying? This is the remainder theorem. That's the answer when I plug it in. Great. The factor theorem is saying, okay, well, if that remainder is a 0, this is also a factor of this polynomial, meaning if I can get it into fully factored form, I would see an x plus 4 as one of those. That's also where it would hit my x-axis when I go to graph it. So putting all of those things kind of together. So they word this very interestingly in your book. So let's look at how they say this. Solve the equation, which is what we did on our warm-up, right? Solve the equation means at the end I'm going to have x equals blah, 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 right? Given that 3 is a 0 of this equation. So first of all, take out the second part of that question, solve the equation. I would have started just like we did in our warm-up. I would have tried to factor and set the factors equal to 0. But do we have a method to factor, and I'm going to erase this in just a second. Do we have a method to factor 2x cubed minus 3x squared minus 11x plus 6? Grouping would be what I try, right? But when I go to do grouping, do I end up with the same thing inside when I take out my GCFs? Well, this doesn't even have a GCF. Right, so this is going to end up being 11x minus 6 if I take out a -1. Doesn't match. Grouping would not work. I don't have a method to factor this. This is when we have to use that factor theorem. And the factor theorem says, if I know a 0 or a factor of my function, when I do this, I'm going to get a remainder of 0. So let's look what happens then when I do that. So I will put the 0 out front. I will do my synthetic division. And I will expect a remainder of 0 because they told me that it is a 0 of this function. And the factor theorem says its remainder is 0 when I divide it. So I would have 2, -3, -11, and 6. I am expecting a remainder of 0 when I get over here because they told me it's a 0 of my function. Okay, so let's go ahead and do our synthetic division. 3 times 2 is 6. Negative 3 plus 6 is 3. 3 times 3 is 9. Negative 11 plus 9 is negative 2. 3 times negative 2 is negative 6. And just as we expected, we get a remainder of 0. Okay, and we anticipated that. Okay, so why is this helping me at all? I know that one of our answers is 3. They told me that. But now, when I divide it, I basically factored that out, and what I'm left over with, write this polynomial. This would be a 2x what? Squared plus 3x minus 2 without a remainder, right? And what you're looking at is factorable, and we should be able to factor this at this point. So use whatever your method is to factor this. I need it to add up to a positive 3 in the middle there. So I'm doing my guess and check. My factors are going to be 2 and 1 again. To get a positive 3, I'm going to get a, let's see, 4 and 1. Positive 4, negative 1. There's the rest of my zeros. Set this equal to 0 and solve. And we already knew that x equals 3 is a 0, right? So as we think about our list, total list of zeros, they told us 3. We're finding the rest of them. So solve the equation. Our solutions are 3, 1/2, and negative 2. They told me that one, which helped me find the rest of them. So what do we use this for? We use this to be able to start the process given something that is not factorable to begin with. Logan? Yeah, my thought process on factoring that. Is that what you're talking about? So I start with the first term and the last term because that's going to fill in the factors of this first term, fill in that first spot. Well, 2 is a prime number. I only have one set of factor options, 2 times 1. So I started there, 2 times 1 to fill in my first spot. The second spot is filled in with factors of our last number. It also happens to be prime, so I only have one set of options. So at that point, it was a guess and check. I left that in there, and I was filling in spots here with factors of 2, which could be 1 and 2 or 2 and 1. But because this is negative, I was trying out all the different signs as well, because this one could be a negative 1 and a positive 2, or it could be a positive 1 and a negative 2. A negative 2 and a positive 1, or a positive 2 and a negative 1. And I just took turns putting those in there and then doing my outsides times my insides to see what would give me an answer of 3. So that's kind of the process of guess and check, like written all out there. I know you guys have some other methods out there as well. And if you need help with those methods, I can help as well. Okay. Other questions on this page? Guess and check goes really fast if you're working with prime numbers. It's kind of when we have multiple options of factors. Like if I'm looking at something like 12, then you have to consider 1 times 12, 2 times 6, 3 times 4, and any of those combinations get in there, and you just keep trying them out until you get the middle term to show up. All right. This one is similar to the one we just did, so I'm going to let you guys work ahead of me on this one. Read the problem, see if you remember how to start the problem. Yes, negative 3 plus 1. Yeah. Yeah, you recognize it? I told you our warm-up was going to show up later. You guys recognizing this one? No, not yet. Not there yet. Okay, the key on factor theorem is remembering that whatever zero they give you is the zero you put outside. And I get that in synthetic division, it can be confusing because when we were handed a factor, we had to use the opposite sign, right? But they are telling us that this is a zero. The number that sits out front of your synthetic division is a zero of your function. So we fill in with 15, 14, negative 3, negative 2. Start my synthetic division process. Negative 1 times 15, negative 15, plus 14 would be negative 1. Negative 1 times negative 1 is 1, plus negative 3 is negative 2. Negative 1 times negative 2 would be 2. Now, I just want to say that I had a great conversation out there, and not to like point this out or anything, but we know the answer should be 0 at the end. And if we are not getting a 0 at the end, something is going wrong. And that is a great thing to catch for yourself, because you're like, hey, something happened. You can't just go fill in a 0 at the end knowing it's at the end, because we need this for a reason, right? But that's a great way to check yourself, knowing that this should be 0 at the end. If it does not end up being 0, something happened along the way. Go back and find the error, okay? Then we take this and we write it into our polynomial, and this is where some of you caught. Yes, this is the reason I did our warm-up. We have to be able to factor this because what we have done is we have factored out the x plus 1 factor, leaving us with something now that we can find actually factor, since we were not able to factor this. So what did we have? 5x and 3x and 2 and 1. We set each of those equal to 0. And again, this was our warm-up, so I will skip that showing our work step. So our solutions, including the solution they gave us at the beginning, negative 1, 2/5, and negative 1/3. So just kind of showing you again, all of this, there we go. Side by side, what we're doing right now is I can't factor this, right? Factor by grouping doesn't work. I can't factor it. They told me that one of the factors of this is x plus 1, which then as a 0 looks like negative 1. And what synthetic division does is tell me, okay, if I take that factor, if I pull that GCF out, or I take that factor out, what I'm left with is 15x squared minus x minus 2. So that if I multiplied that all back out, we'd get to here. Basically, they're doing the first step of the factoring for us. We use a synthetic division to see what's left with that. And then you're at this step right here of continuing to factor that part of it to get a fully factored form to find all your solutions. Any questions? All right. I want to go ahead and try these two. So if you will grab your dry erase markers, we are going to go to our check for understandings here at the end. While you're getting your dry erase markers out and doing this problem on your table, I'm going to stop my